Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be learning all about the different types of chillers available, their applications, as well as their limitations. Now before we jump in, I just want to take a moment to thank our partner Danfoss for sponsoring this video. Danfoss have been creating solutions for chillers for a long time, and they have a broad range of high quality products available for all chiller types. In fact, they have up to 70% of the products you need for your chiller system, including compressors, AC drives, system protectors, heat exchangers, valves, electronics, and sensors. All of these solutions help you create better chillers from the inside out. To find out more, visit chillers.danfoss.com. If you're working within commercial refrigeration, especially chillers, or you're about to start, perhaps you're a student or an apprentice, maybe you're a building manager or an architect, etc., then you're going to hear engineers say things like the recip, the turbo core, the towers, etc. You might not have any idea what they're talking about. If so, don't worry, because by the end of this video, you will. Now, we've covered how these chillers work in great detail previously. Links are in the video description below, and if you're not already a subscriber, then hit the subscribe button now and we'll help you become an expert. Just to recap you on your previous knowledge of chillers, chillers are simply machines used to generate cold or chilled water which is distributed around buildings to provide air conditioning. They are also used in some industrial processes, but we're going to primarily focus on their application in air conditioning of buildings within this video. As you can imagine, there are a lot of different types of chillers and they are categorized by types. So it's important you understand what the names mean, the differences between them, when and where they are used, as well as why. The first way to categorize a chiller is by defining whether it is a vapor compression or a vapor absorption type chiller. Vapor compression chillers use an electrically driven mechanical compressor to force the refrigerant around the system. These are the most common type of chillers. There are two subcategories for vapor compression chillers, which are water-cooled or air-cooled chillers, and we'll look at these both shortly. The other main category of chiller is the vapor absorption type. Instead of using an electrically powered mechanical compressor, these units use heat to move the refrigerant around the system. Coming back to vapor compression chillers, the two main types we said were air-cooled and water-cooled. Now both types of chillers have the same essential components, which are the evaporator, the compressor, the condenser, and the expansion valve. When we talk about air or water-cooled, this simply refers to the way in which the unwanted heat is ejected from the building via the chiller's condenser. The working principle for both air-cooled and water-cooled chillers is essentially the same. A compressor pushes a refrigerant around the inside of the chiller between the condenser, the expansion valve, the evaporator, and back to the compressor. The only difference is that with an air-cooled chiller, fans force air across the exposed tubes of the condenser, which carries the heat away, whereas with a water-cooled chiller, this has a sealed condenser and water is pumped through this condenser to take the heat away and disperse this through the cooling tower. The cooling tower will use a fan to reject the heat also. So, where are these chillers typically used? Large buildings with cooling loads in excess of around 400 tons or 1400 kilowatts typically use water-cooled chillers, and they'll usually be centrifugal type or turbo core type compressors within the central plant cooling system. They might also use a separate smaller air-cooled chiller to handle the cooling loads of critical rooms such as computer and communication rooms. There might also be an absorption chiller within the central plant system, making use of waste heat from maybe a CHP engine for example, but these are mostly used alongside mechanical chillers. Medium-sized buildings with cooling loads of around 200 to 400 tons or 700 to 1400 kilowatts will typically use screw compressors or turbo core compressor chillers. Now these chillers can be either water-cooled or air-cooled, and we'll look at why that would be just shortly. These types of buildings might also use an absorption chiller if enough high-quality waste heat is available. Smaller buildings with cooling loads of around 200 tons or less or 700 kilowatts will typically use scroll compressors or even turbo core compressors, and these are mostly going to be air-cooled design. Again, we'll look at why that will be just shortly. They might also use a completely different system such as a VRF unit, but this really depends on the size of the building and the cooling load. If you have a building with a medium to large cooling load, then it's recommended that you do not use only one oversized chiller to handle the entire cooling load. This is not efficient, and if it fails, you will have no cooling capability left. Instead, you should use multiple chillers in parallel of different sizes to meet the changing seasonal load at optimal performance with redundancy built in. For example, you have a building with a cooling load of 2,200 tons, then you should use combinations such as two 1,200 ton chillers, or two 900s and a 500 ton chiller, or 1,000 ton and two 700 ton chillers, etc, etc. The options are almost limitless. You also need to consider the criticality of the building and the redundancy required, which is known as the N+ number, where the N is the number of chillers you need and the +1, +2 or +3 etc is the number of backup chillers you need to be able to continue to meet the cooling capacity in the event of a failure, so that if any chiller fails, you always have a backup ready to come online and take over to handle the cooling load. You might need to use chillers with multiple compressors that can work independently from one another, so that if one compressor fails, then the chiller can still remain partly operational. Unfortunately, many building owners want the cheapest upfront option, but this is a bad idea because for a little extra, they could have bought a more efficient chiller which would be cheaper to operate, especially as chillers last around 15 to maybe 25 plus years in operation, so it would have paid for itself multiple times and would have resulted in reduced environmental emissions. So how do you decide between choosing an air-cooled or water-cooled chiller? Well, this really depends on a lot of factors, so let's have a look at the pros and cons for both of them. Now, some of the pros for using water-cooled chillers is that water-cooled chillers are typically more efficient, especially for larger cooling loads. They use the evaporation of water to dissipate the heat, which is obviously going to be less energy intensive than blowing air across a hot surface like air-cooled chillers do. Water also has a higher heat capacity than air, so it's inherently easier to remove the heat. Water-cooled chillers can also handle larger loads for their floor space that they consume within the building, and water-cooled chillers generally last longer because they are held within the building, so they're going to deteriorate much slower. So some of the cons to using water-cooled chillers is that these type of chillers use cooling towers, and for this you need access to a constant supply of clean water. If the chiller is therefore going to be installed in an area of water restriction or conservation, then you won't be able to use this type of chiller. Water-cooled chillers are located within the building and they are very large machines, so depending on the compressor technology used, they can create a lot of noise and vibration inside the building, which is why they are usually located in the basement. Water-cooled chillers do cost more to install and also to maintain. Water-cooled chillers take up space within the building. They need more mechanical plant rooms, more risers, more pumps, more cooling towers and water treatment facilities. This space therefore can't then be used for business purposes. Let's now have a look at air-cooled chillers. So some of the pros for using air-cooled chillers is that they cost less to install, and that's because they use less equipment. Air-cooled chillers require less space. They can sit up on the roof or out in a car park, and they do not need a mechanical room. This means more space within the building for business purposes. Air-cooled chillers require less maintenance compared to water-cooled chillers, again because they have less equipment. Air-cooled chiller systems are much simpler and easier to design and do not need another set of pumps for the condenser loop. Some of the cons for using air-cooled chillers is that air-cooled chillers sit outside the building. Their fans and compressors will create noise which the surrounding areas might be able to hear, although some measures can obviously be implemented to reduce this. Air-cooled chillers typically do not have as long service life compared to water-cooled chillers because they are exposed to the sun, the rain, the frost, the snow, the wind, etc., and this will all deteriorate the materials. Air-cooled chillers can suffer from blockages much easier. They can be damaged and they can also suffer from things like recirculation issues. So let's now have a look at some of the different compressor technologies that are currently available. Centrifugal chillers are used for water-cooled chillers. It's incredibly rare that you would come across an air-cooled centrifugal chiller. They are used in medium to large cooling loads, typically available from 150 up to 6,000 tons of refrigeration, or 530 to 21,000 kilowatts. They have a COP of around 5.8 up to 7.1. Typically they'll use only one compressor, sometimes two for exceptionally large capacities. They work best at full loading, although VFDs can be fitted to improve the part load performance. They'll use one or two rotating impellers to compress the refrigerant and force it around the chiller, and the capacity can be controlled through speed control as well as vane guides. Turbo core compressors represent the latest in chiller compressor technology, and they are an evolution on the centrifugal type compressor. And this is definitely something to keep an eye on as they are becoming more common, and you're going to start to see these more and more in buildings. Turbo core compressors can be used for air or water cooled chillers, and they are used in all cooling loads from large to small buildings. They're typically available in 60 to 1500 tons or 210 to 5200 kilowatts. They have a COP of 4.6, even up to 10. They have one or more compressors which are used, and they can be staged or the speed can be varied. They have variable speed controllers. They have soft starters, magnetic bearings, and they only have one moving part. They are oil free and very low maintenance. They use rotating impellers to compress the refrigerant, and the capacity can be controlled through speed control as well as vane guides. Reciprocating compressors were used for air or water cooled chillers, although this is an older technology which is far less common now. They're used in small to medium cooling loads, although now the technology is much more common in simple, smaller, low-cost refrigerators and refrigeration systems. For chillers, they're typically available from 50 to 500 tons or 170 to 1700 kilowatts. They have a COP of around 4.2 to 5.5, and they use a piston and chamber to compress the refrigerant. The capacity is controlled through the compressor staging, cylinder unloading, as well as the speed control. Scroll compressors are used for air or water cooled chillers. They are used in small to medium cooling loads, typically available from around 40 up to 400 tons or 140 to 1400 kilowatts. Air-cooled chillers typically have 3.2 up to 4.6 COP. Water-cooled COPs might be 4.45 up to 6.2. They'll use one or more compressors, which can be fixed or variable speed, and they can be stage or speed controlled. They use two spiral plates to compress the refrigerant. One will be fixed in place and the other one rotates. Capacity is controlled via momentarily separating the scrolls using a solenoid valve and electronic modulation. Screw compressors can be used on air or water cooled chillers, and they are used in small to medium cooling loads. They're typically available in 70 up to 600 tons or 250 to 2100 kilowatts. The air cooled screw compressors will typically have a COP of around 2.9 up to 4.15. Water cooled will have a COP of 4.7 up to 6.07. Typically they'll have one compressor on a water cooled chiller or 1 to 2 compressors on an air cooled chiller. They use two interlocking rotating helical rotors to compress the refrigerant, and the capacity is controlled via speed control or a slider. Absorption chillers. Now these use heat to drive the refrigeration process. They usually use steam or hot water. They're used in medium to large buildings such as hospitals, swimming centers and heat networks, and they're ideal for using waste heat or at least cheap heat, and they're sometimes used to offset peak electricity cost. They typically are combined with mechanical chillers though. Now typically you can buy these from 70 to 1400 tons or 250 up to 4900 kilowatts. They have a very low COP of 0.6 up to 1.9. They have no compressor. They are either direct or indirect fired, and capacity is controlled simply by varying the amount of heat which is entering the chiller. That about wraps things up, but before I go, I just want to thank Danfoss one last time for sponsoring this video. Don't forget to check out their wide range of chiller solutions over at chillers.danfoss.com. Thanks for watching. I hope this has helped you and you've enjoyed it. If so, please don't forget to like, subscribe and share. Also follow us on Facebook, Twitter, Google+, and Instagram, and check out our website, theengineeringmindset.com. Once again, thanks for watching.